Hey guys, so in the last lesson we talked about how an impulse or an action potential is transmitted down the length of an axon until it reaches the axon terminal. Today we're going to talk about what happens once that impulse has reached the axon terminal to move that signal from one neuron to the next. So in this lesson called Synapses, we're going to be going over what synaptic transmission is and how it works. We're going to talk about the effects of neurotransmitters on the postsynaptic cell. You need to know different ways that neurotransmitters can be stopped and why that's important. You need to know what different neurotransmitters do and what could happen if there's too many or too few neurotransmitters. And then we're going to briefly touch on the effects of depressants, stimulants, and neurotoxins on the process of synapses. So synaptic transmission is essentially how an impulse is moved from one neuron to another. A synapse is both the process of moving that impulse from one to another, and it's also the small gap between neurons. So to avoid confusion, we usually call the space between the neurons the synaptic cleft. An action potential or an impulse is going to travel down the axon until it hits the end of the axon, which is called the axon terminal. Then it has to move from the axon terminal of one neuron to the dendrites, which is like the little finger projection parts of the next neuron. So the neuron 1, axon terminal, space between the neurons is the synaptic cleft, and then we have the dendrites of our next neuron. The first neuron, the one that has the axon terminal right before the synaptic cleft, that is called the presynaptic cell because it's before the synapse. And then the neuron that is after the synaptic cleft, that has the dendrites there, that is the postsynaptic neuron because it is after the synapse. Okay, so neurotransmitters are little chemicals that are going to diffuse from the axon terminal across the synaptic cleft to the postsynaptic neuron's dendrites. The cell membrane of those dendrites are going to contain little receptors that will grab the neurotransmitters as they come across the synaptic cleft. Okay, so the axon terminal contains what are called synaptic vesicles. So the vesicles are just little tiny pouches, little circular pouches, and inside the vesicles are the neurotransmitters, those little chemicals. And so what happens is when the action potential reaches the axon terminal, those little vesicles are going to bind to the outer membrane of the axon terminal and release the neurotransmitters into the synaptic cleft. That's exocytosis, if you remember that from Science 10. Okay, so this is kind of what it would look like. If we look at this top neuron right here, this would be the presynaptic neuron. The action potential moves down the axon until it reaches its axon terminal. Then that's going to cause the neurotransmitters to be released into the synaptic cleft, the space between the neurons. And then those are going to float across until they hit the postsynaptic neurons' dendrites. Okay. If we kind of zoom in here, you can see what's happening a little bit better. So this would be the axon terminal of the presynaptic membrane. These little circles here are the vesicles. The little black dots inside of them are the neurotransmitters. And so what'll happen is once the impulse travels down the axon and gets to this axon terminal, some of those vesicles are going to bind to the outer membrane of the axon terminal and release their neurotransmitters into the synaptic cleft. And then those neurotransmitters float across the synaptic cleft until they get to the receptors right here on the postsynaptic membrane. So this is like a really close-up of like the end of a dendrite on the postsynaptic membrane. And these are the little receptors. Okay, impulses cannot just jump from one neuron to the next. It's too far of a jump. And the reason that we have those gaps, like the reason it's not just all going down an axon, is to, first of all, ensure that the impulse only goes one direction, but also to allow an impulse to spread out more. So when you have this impulse jumping down and it gets to the axon terminal, you could have more than one postsynaptic neuron. And so that signal could be sent to two different postsynaptic neurons to spread out the signal to send it to multiple areas at once. It also allows unimportant background stimulus to be filtered out. And the reason for that is that sometimes when those neurotransmitters go across and hit the postsynaptic membrane, sometimes that causes an impulse to be sent in that next neuron, and sometimes it doesn't. And we're going to talk about how that works. But when it doesn't, it's because it's filtering out some of that unimportant background stimulus. So that would be like, you know, if you've ever had like your glasses on your head or like a pen behind your ear, and then you're going like, where's my pen or where are my glasses? Because you don't feel them there anymore. That's because you have filtered out that information as unimportant background information. Essentially what had happened is the like neurotransmitters in, say, your scalp were sending information like, I feel something on my head, I feel something on my head, I feel something on my head. And you weren't doing anything about it. You were just leaving your glasses on your head. And so eventually your neuron said, this must not be important information because they're not doing anything about it. So I'm just going to stop sending that information. And then you really stop feeling that there's anything on your head. I do this all the time where I have like my phone sitting on my lap. And when I first put it there, I can feel it, of course. And then eventually that becomes filtered out background noise that my neurons stop processing. So I stop feeling it. And then I stand up and my phone drops to the ground. And I do that a million times a day. So all of this comes down to the effects of those neurotransmitters on the postsynaptic membrane, the one with the dendrites. The neurotransmitters can have two possible effects. You can either have excitatory neurotransmitters or inhibitory neurotransmitters. Excitatory neurotransmitters are going to excite the postsynaptic membrane. Essentially, what they're going to do is cause that postsynaptic membrane to start to depolarize so that it can have its own action potential. So think back to our action potential lesson. So if you remember, in order to have an action potential, you have to have some sort of stimulus, then some of the sodium channels open, and then you hit the threshold, and then all of the sodium channels open, the membrane fully depolarizes, and you have an action potential. And then it repolarizes with the closing of the sodium and the opening of the potassium channels. So if you have an excitatory neurotransmitter, leaves the axon terminal, goes across the synaptic cleft and binds with the receptors on the postsynaptic membrane, it's going to cause the postsynaptic membrane to open up the sodium channels. The sodium flows in, it depolarizes that postsynaptic membrane, and it's going to have its own action potential, which then gets sent down its axon to its axon terminal. So it's just essentially the neurotransmitter is the stimulus that causes an action potential in the next neuron. Or you can have an inhibitory neurotransmitter. An inhibitory neurotransmitter is going to hyperpolarize the postsynaptic neuron. So it's making sure that absolutely no signal is getting sent from that postsynaptic neuron. It's hyperpolarizing it. So it's putting it in the opposite direction of an action potential. It's essentially putting it into a refractory period. So usually how that works is the neurotransmitter goes across the synaptic cleft, it binds with the postsynaptic neuron, and it's going to cause potassium channels to open. Potassium goes in, causes that membrane to hyperpolarize, no more signal is getting sent. That is when essentially your neurons have decided this is unimportant background noise, we're not going to send the signal to the brain anymore. Okay, so in order for more impulses to reach and affect the postsynaptic neuron, the effects of the neurotransmitters have to stop quickly. You don't want the exact same signal constantly being sent to the postsynaptic neuron just because some neurotransmitters were like slower getting across. So you need to kind of get those neurotransmitters out of the synaptic cleft after they've done their job, or after some of them have done their job, so that a new signal can get sent. So there's 3 ways to stop neurotransmitters. Some of them can be broken down with enzymes. Some of them will just diffuse out of the synaptic cleft. And then sometimes you'll have astrocytes, which are a type of glial cell that carries the neurotransmitters back to the axon terminal. So this is called reuptake. Essentially, these cells go out, they grab any neurotransmitters still in the synaptic cleft, bring them back into vesicles in the presynaptic membrane in the axon terminal. So again, they can be used later. Okay, acetylcholine is a neurotransmitter that excites skeletal muscles, so it causes them to depolarize, have their own action potentials, and it essentially causes the muscle fibers in the skeletal muscles to contract. It also inhibits cardiac muscle, so it stops cardiac muscle, so your heart muscle, from contracting. Cholinesterase is an enzyme that goes out into the synaptic cleft and it breaks down acetylcholine. It's a really fast-acting enzyme to get rid of the acetylcholine really quickly, which is super important because if you didn't have this enzyme, muscles like your heart, where that cardiac muscle is, or even your diaphragm, which is what allows you to breathe, could become like paralyzed, so could stop working. It could also, like, if your muscle cells are like constantly contracted, that would also be bad, obviously. So you don't want your muscles to be constantly contracted. You don't want your heart to stop contracting. So you need this enzyme cholinesterase to break down the acetylcholine really quickly after it's done its job. There are some nerve gases and some insecticides which actually inhibit this enzyme. So the acetylcholine keeps stimulating the postsynaptic membrane, which can cause constant muscle contraction of the skeletal muscles or inhibit your cardiac muscles, which can lead to death. So it is, very dangerous. Obviously, nerve gas sounds dangerous. Norepinephrine is a neurotransmitter that stimulates the sympathetic nervous system, which is the part of your body that responds to stressful situations. Also really important in forming memories. The effects of norepinephrine are stopped by reuptake as well as some enzymes breaking them down. If you have too much norepinephrine and it's not being taken out of the synaptic cleft fast enough, it can lead to things like anxiety because your body's constantly preparing for some sort of stressful situation, even though you're not in one. It can also lead to insomnia, because people have a hard time sleeping when they're feeling very stressed, high blood pressure, that kind of stuff. If you don't have enough norepinephrine, then you can be very apathetic and tired all the time because you're not feeling stimulated enough by your surroundings to be excited about anything. So a lot of time, I mean, it's not just norepinephrine. We have a lot of different neurotransmitters in our brain that affect like our mood, our level of anxiety, our level of happiness, all of that kind of stuff. So when people are taking like anti-anxiety medication or antidepressant medication, it's usually to compensate for issues with these types of neurotransmitters where perhaps they're not being degraded by enzymes fast enough, or they're being degraded too quickly or something like that. There are also substances like drugs, different chemicals, neurotoxins that can interfere with the function of your neurotransmitters. And depressants and stimulants are two categories of substances that can affect your synapses in different ways. So depressants essentially slow down messages that are moving between the body and the brain. Any signals that are coming from your sensory receptors will reach the brain more slowly. Your heart rate drops, so your body is receiving less oxygen, so your energy levels drop. Your breathing rate decreases, which also increases your rate of risk of lung infection. Messages to the muscles from the brain, so brain to motor neurons to effectors, all of that is moving really slowly, so you can respond to the environment more slowly, you're moving more slowly, and essentially you become less able to both sense and respond to any dangers and stuff like that. So like alcohol is an example of that. That's why you're not supposed to like drink and drive, because you can't respond to the environment quickly enough. You can't sense danger quickly enough, and you can't respond to it quickly enough. Stimulants are the opposite of that. They actually create fake messages that get sent to the brain that's telling the brain that the body is experiencing some sort of stress. The brain is sending these stress signals back to like your heart and your lungs and different like glands that secrete like stress hormones and stuff like that. Blood to skin decreases because it's funneled to your central organs. So the body is less able to cool itself. People tend to overheat more quickly. Your heart rate speeds up. Your blood vessels constrict, which increases your blood pressure. Sugars that are stored in the liver get released into your blood. So your blood sugar goes up. And then if a real stress occurs, your body is unable to respond to it because it's already kind of wasted all of its energy on this like fake stress situation. Okay, neurotoxins are substances that are poisonous or destructive to nerve tissues. They inhibit neuron control over the ion concentration, so like sodium and potassium and stuff like that, and also inhibit the neurotransmitters, so communication isn't working across the synapse. Many interfere with muscle contractions, which can like stop the heart or stop the diaphragm, which means you can't breathe, which can cause death. That includes things like ethanol, snake venom, botulism, which is like Botox, Purare, stuff like that. Okay, that is it for today's lesson. Please let me know if you have any more questions about this stuff, especially like synapses and excitatory and inhibitory neurons.